Welcome to this explainer. Today we're diving into something absolutely mind-bending. Literally, we are exploring the physics of bending space and time to create cosmic shortcuts. We're tackling the unimaginably vast problem of interstellar travel and the physics that might actually solve it for us. When we look up at the universe, the sheer scale of it is just incredible, right? But it's also deeply frustrating, because even if our telescope spotted a perfect Earth-like planet in another galaxy tomorrow, getting there, that's a massive problem.
Okay, let's put this problem into perspective. We all know Earth is here in the Milky Way, and our closest galactic neighbor is Andromeda, sitting about 2.5 million light-years away. If we jumped into a modern spacecraft right now, cruising at a usual top speed of around 28,000 kilometers per hour, it wouldn't just take a long time to get there, it would take an agonizing 94.5 billion years. Think about that for a second. That is literally older than the universe itself.
Now you might be thinking, well, what if we just upgrade our tech? Okay, let's say we pull off a miracle and engineer a ship that travels at the absolute speed limit of the universe, the speed of light. Even then, it still takes 2.5 million years to reach Andromeda. So conventional space travel is practically impossible for any human lifespan, which really begs the question, what is the point of finding new planets if we can never, ever reach them?
Section 1. Bending the space-time mesh. To find a way out of our galaxy, we desperately need a shortcut. You might remember the movie Interstellar from 2014, where the crew travels to another galaxy in just a few minutes. Sounds like pure Hollywood magic, right? But we're going to look at actual astrophysics today to see why this isn't just a sci-fi fantasy, but a concept grounded completely in real science. Let's look at the timeline here to see how this all builds. It starts back in 1915 with Albert Einstein's field equations. He completely flipped how we view the universe by proposing that space and time act together like a massive invisible mesh. If you drop a heavy object on it, like a star or a planet, the mesh bends and curves under the weight. The very next year, in 1916, Carl Schwarzschild solved these equations to mathematically prove black holes exist. And then by 1935, Einstein and his assistant Nathan Rosen stumbled upon a mathematical solution for something even stranger:
a wormhole. The crucial takeaway here is that wormholes aren't just some made-up sci-fi trope, they are a direct mathematical solution to Einstein's field equations. You might wonder, wait, how can one set of equations give us both black holes and wormholes? Well, it's kind of like a quadratic equation from high school math, where x equals 2 and x equals 3 can both be correct answers. The math says both can absolutely exist in our universe.
To visualize how this works, picture a flat piece of paper with two dots, A and B. In a 2D flat world, the fastest route is a straight line drawn between them. But what if you bend that paper through a third dimension? You fold it so A and B are touching, and then bam, punch a hole straight through. Suddenly, you've got an ultimate shortcut. It's exactly like how a flight from Delhi to New York looks like a huge sweeping curve on a flat 2D map, but when you look at a 3D globe, flying up New Greenland is actually the shortest straight line. A wormhole does this exact same trick, just bending our 3D space into a fourth dimension. Section 2. The Einstein-Rosen bridge. So what is the actual scientific identity of these shortcuts? Formally, they're known as Einstein-Rosen bridges, named right after the two guys who pulled them out of the mathematical ether in 1935. But honestly, Einstein-Rosen bridge is a bit of a mouthful, so in 1957, physicist John Wheeler published a paper using this brilliant analogy. He said, imagine an apple, and there's an ant crawling on the surface. For the ant to get to the exact opposite side, it has to walk all the way around the circumference. But a worm just chews a tunnel straight through the core, drastically shortening the trip. He coined the term wormhole, and it was so perfect, the name just stuck forever. Now, if you Google wormholes, you'll usually see them drawn as flat circles on a grid. But because a real wormhole exists in 3D to 4D space, it wouldn't be flat at all. It would actually look like a spherical ball. As you fly into it, you'd see the universe completely wrapping around you. And here is where it gets absolutely wild. If you bypass millions of light years in an instant, you'd arrive at your destination before the light from Earth could even reach it. Yep. That means a wormhole isn't just a space shortcut, it's essentially a theoretical time machine.
Section 3. Black holes to white holes. But, as always, there is a catch. You can't just wish one of these space-time tunnels into existence. To bend the fabric of reality that extremely, you need an unfathomable amount of gravitational force.
Einstein and Rosen theorized there's only one thing out there strong enough to rip open a tunnel like that, a black hole. Since everything is attracted to a black hole, matter could certainly flow into this tunnel. But we really have to ask, what exactly is waiting on the other side? If it's just another black hole at the exit, well, that's not a gateway. That's a dead end. You'd be permanently trapped and ultimately crushed. Enter Russian physicist Igor Novikov. In 1964, he proposed a brilliant theoretical solution, the white hole. It's the exact mathematical opposite of a black hole, in literally every single way. A black hole has an event horizon of no return. A white hole has an event horizon of no ignition. Nothing can go inside. Instead of sucking in all light, it blasts out blinding white light. Instead of destroying matter, it spits it out. Basically, a white hole serves as the ultimate cosmic exit door to our wormhole.
Section 4. The entropy problem. Sounds perfectly neat and tidy, right? Well, not quite. White holes have actually sparked this massive, ongoing debate among modern physicists. They basically cause a head-on collision between two foundational areas of science, quantum mechanics and the laws of thermodynamics.
On one side of the ring, we've got quantum mechanics. Stephen Hawking theorized that black holes actually slowly evaporate over time by leaking radiation. But quantum theory has this strict rule called the no-hiding theorem, meaning quantum information can never be permanently deleted from the universe. So if a black hole dies, all the stars and planets and information it swallowed have to go somewhere. A lot of physicists argue this trapped matter is eventually spat back out into the universe, potentially through a white hole.
But on the other side of the ring, we have thermodynamics. The second law of thermodynamics states that entropy, or disorder, must always continually increase. Always. Think of a black hole like a giant cosmic paper shredder, grinding planets down into messy, disordered radiation. A white hole would be reversing that process. It would be like watching the paper shredder spit out a perfectly reassembled, readable document. Try to imagine how absurd that would look. That's exactly why thermodynamics makes white holes so controversial. By our current understanding of physics, reducing entropy like that is physically impossible.
Yet despite all this heavy theoretical debate, we might have actually seen one. On June 14, 2006, the Swift Observatory caught this massive, completely unexplainable explosion of white light out in a distant galaxy. Now, normally, these gamma-ray bursts happen when a black hole eats a star. But in this specific event, which they call GRB 0660614, there were absolutely zero star remnants to be found. The light just burst out of nowhere and vanished. To this day, some scientists hypothesize that they briefly caught a real physical white hole on camera.
Section 5. The future of travel. So while cosmic wormholes and white holes are still highly theoretical out in deep space, human engineering is already pulling these mind-bending concepts off the chalkboard and right into the laboratory.
Get this, in 2015 we actually built one, not with gravity, but with magnetics. Scientists took a high-temperature superconductor called yttrium-barium copper oxide, dunked it in a liquid nitrogen bath, and successfully created a lab-made magnetic wormhole. They physically separated a magnet's north and south poles, making the magnetic field disappear at one end and magically reappear at the other through an invisible gap. We literally proved we can actively bend magnetic fields through a wormhole device. And hey, wormholes aren't even the only shortcut on the table. Back in 1994, theoretical physicist Miguel Alcubierre found another mathematical loophole derived from Einstein's equations. It's known as the Alcubierre derive. The idea is that a spaceship could achieve faster-than-light travel without actually moving fast itself. Instead, the ship would physically contract the space-time mesh in front of it and expand the space-time behind it. It would basically be surfing a ripple in reality itself.
Look, the sheer vastness of the universe is definitely intimidating. But remember this, black holes were considered pure mathematical fiction for a full century before we finally snapped a photo of one in 2019. The equations were right long before our tech could catch up. So, with lab-made magnetic wormholes already existing and actual blueprints for space-time drives being drawn up, it leaves us with one incredibly provocative question. How long until human ingenuity finally masters the mesh of space-time, and we take our very first real shortcut into the universe?